So let us start now, Natalie. Um, Welcome to our third series of the EXIT webinar done by the EXIT scholars. We welcome Natalie Zimmer. She's an undergraduate student at Luisiana State University. Her major is physics and astronomy. Her research advisor is Micheal Cherry from Luisiana State University. Okay, welcome, Natalie.
Hi. So my project is using GEANT4 for transition radiation simulations to reduce the proton Kaon contamination level. So can y'all see if I scroll down with this?
Yes, let me just zoom in a little bit.
Okay.
You can use these arrows right here. Next slide.
Okay. So let's start with what is transition radiation? Transition radiation occurs when you have a high energy charged particle pass through different media with two different dielectric constants. And this happens because of a collapse in the particle's electromagnetic field, and it throws off a photon with an energy that's the difference between, well, it's related to its Lorentz factor, which is a relativistic component that has to do with how the particle's properties change as it becomes, approaches the speed of light. Transition radiation is mostly directed in the forward direction, and it peaks at an angle on the order of 1 over the Lorentz factor relative to the particle's path. And so as you can see in the picture here, we have a charged particle labeled as beam coming in from the left side, going through a radiator, which is many different foils. And like I said, they'll have a different dielectric constant than the air, or if it's in a vacuum, then the vacuum. And then the transition radiation will be thrown off, and you see that labeled TR. And then it will be picked up in a gas detector, which is usually either xenon or krypton. and the gas detector will pick up the energy of the particle or of the photon that is deposited in it. So that's how transition radiation happens. And currently at CERN, there has been set aside time for a experiment for proton-proton collisions and proton-heavy ion collisions in the very, very forward direction, which is the region where your secondary particles fly off at very low angles relative to your primary particles. So, everything goes mostly in the forward direction. And like I said, transition radiation also goes in the very forward direction. So that's useful here. And transition radiation is actually the only way to identify between high energy protons, pions, and kaons. And so, like I said, these protons, pions, and kaons, these are charged particles that when they're produced in the proton-proton and proton-heavy ion collisions, they will go through transition radiation detectors and create photons, which we can detect and then tell if the photon was created by a proton, pion, or kaon, judging by the energy level that's deposited in the detector. So currently we can identify pions fairly well. 1 in about 10 to the 4 will be misidentified, which that's our goal. But currently, we can only identify protons and kaons as with an accuracy of about 1 in 10 to the 2 being misidentified, which this is a factor we need to improve in order for this experiment to move forward, because we cannot go on with that contamination level because you don't have accurate data for, which is a proton and which is a kaon. And so how we're going to do this is we need to maximize the photon production in the space that's been allocated for our transition radiation detectors at CERN, because if we can produce more photons, then we'll have more energy being deposited, and we'll have statistically more data that we can identify between what would be caused by a proton between what would be caused by a kaon. And so we have 8 meters of space at CERN that we can that's been allocated for transition radiation detectors. And so that's where these simulations come in. I'm using GEANT4, which was actually developed by CERN for reasons like this, for, quote, the simulation of the passage of particles through matter. So what I'm doing is I'm simulating charged protons, pions, and kaons passing through transition radiation detectors or radiators into a gas chamber where, like I said, the energy of the photon that's produced from the transition radiation will be picked up. And we can tell by the deposited energy if your particle was a proton, pion, or kaon. So I've coded in GEON a physical structure that resembles what we're going to have at CERN, ideally. GEON is written in C++, so that's what most of the coding is in. It's really useful because it has built-in databases, like NIST has a materials database. It has all your properties and equations for all of your particles and all of your materials have pre-made dielectric constants, which you can go in and change if you need to for some reason, but it's there so that you don't personally have to go and define all these things that aren't what you're trying to focus on. So like I said, we've created a simulation that resembles our space at CERN. So within 8 meters, we're trying to create the most photons so that, like I said, we can create energy spectra and tell which particles are protons, pions, and kaons. And so similar things have been done in the past, which my advisor conveniently wrote some papers on, so we can compare our energy spectra that we're producing with some past experimental results. And so that's what I'm doing currently. This is a little flowchart of GEANT. I don't have to edit all of this. The so the little dot means GEANT like uses, and then whatever's below it. So like GEANT uses readout, which uses run, which uses events. These are all different components of GEANT that you can go in and edit, and like it looks pretty complicated because it is. But thankfully, I really only have to edit the geometry, which is pretty far towards the bottom on the left, processes, and the readout. So let's continue. Okay, so recently we've added Compton detectors on the side of our transition radiation detectors. If you aren't familiar with Compton radiation, it happens when an incoming photon knocks into matter and scatters an electron and a lower energy photon. And so, like I said, when we have particles going through the transition radiation detectors, they're going to be producing photons. But all of them, what if they hit an electron? And then they're going to fly off to the side and we need to detect this. So that's what the Compton detectors are for. They're going to be a centimeter of sodium iodide and run alongside the radiators. That way they'll catch whatever doesn't fly into the gas chamber detectors. And that's what I've just recently added into my project. So here's a picture to kind of help visualize that. Imagine your incoming particles coming from the left side, and this picture is from a past experiment, so not all of it is relevant, but comes in from the right side or from the left side, traveling to the right, passes through the radiator, and then what you see labeled as MWC is a gas chamber detector, which will be read out like it says here, and that is the energy deposits that we look at. And so where the Compton detectors are, they'll be paralleling the top and bottom of the radiators, so that, like I said, any photons that are, or any Compton scattering that happens in the radiators that doesn't go into the gas chambers will be picked up by the Compton detectors. Okay, so now we have simulations. We read out the
Daniel, do you have a phone number that I can call you?